Hello, I am Jinpyo from Seoul National University. This presentation will be about SnuHPL, high-performance LINPACK for heterogeneous GPUs. It is joint work with Hyungdal Kwon, Jintaek Kang, Jihwan Park, and Seungwook Lee from Samsung Advanced Institute of Technology, and my advisor Jaejin Lee from Seoul National University. SnuHPL is a shorthand for Seoul National University's high-performance LINPACK benchmark. It is an optimized HPL for clusters of modern heterogeneous GPUs. In this work, we present three kinds of HPL optimizations. First, inter-process optimization to run efficiently on modern homogeneous GPUs. Second, intra-process optimizations to improve efficiency on heterogeneous GPUs. Finally, we present a simple energy optimization technique to improve the energy efficiency of HPL. HPL is a de facto standard benchmark to measure a cluster system's floating point computation performance. It serves n linear equations of order n, which is to obtain the solution vector x of ax equals b problem. The HPL benchmark is used in top 500 and green 500 lists to measure the supercomputer's performance and energy efficiency. To solve the linear equations, HPL first performs LU factorization on the coefficient matrix, then runs backward substitution to obtain the solution vector. Here, LU factorization takes an order of n cubed floating point operations, but backward substitution only requires an order of n squared floating point operations. Therefore, we usually focus on LU factorization when optimizing the HPL benchmark. In HPL, many processes cooperate to solve LU factorization by a right-looking algorithm with partial pivoting. It iteratively factorizes leftmost NB columns until the factorization of the whole matrix is complete. Here, NB is a tunable parameter of HPL that determines the step size of the algorithm. Left NB columns of not yet factorized part is called a panel, and the rest of the matrix is called trailing submatrix. HPL arranges the MPI processes in a 2D grid of size P times Q. Then distributes the coefficient matrix to the processes in a block cyclic strategy. It divides the matrix into NB times NB square blocks, then the blocks are distributed in a round-robin manner. Every process gets almost the same amount of matrix, and the ratio of submatrix size is also kept the same as the LU factorization progresses. Hence, it is obvious that block cyclic distribution is optimal for homogeneous processes. Now I'll explain how the processes cooperate in running on iterations of the LU factorization. An iteration of LU factorization consists of 4 phases: panel factorization, panel broadcast, row swapping, and trailing submatrix update. From now on, I'll call these phases shortly fact, bcast, swap, and update. First, the fact phase factorizes the panel in the current iteration. Only the P processes that own the panel participate in the phase. The characteristic of the fact is that it consists of small and many blocks and MPI routines. Second, the bcast phase broadcasts the factorized panel to the processes which do not own it. The broadcast is done row-wise in the process grid, where the process that owns the panel becomes the root of the broadcast. Bcast is a relatively simple phase since there is only one large MPI broadcast operation. Third, the swap phase swaps the rows of its trailing submatrix according to the pivot indices, which were used to factorize the current iteration's panel. While it swaps the rows, the upper NB rows of the submatrix are broadcast column-wise. The swap phase consists of large MPI communication operations. Finally, in the update phase, every process updates its trailing submatrix with DTR SM and DGEN routines, so the trailing submatrix become consistent with the factorized panel. There is no inter-process communication in the update phase, and almost all the floating point computation of HPL is done in the update phase. Now, I'll explain the differences of the original HPL and SnuHPL. The original HPL is designed for homogeneous CPU-only systems. There is no GPU support, and its block cyclic data distribution is only optimal for homogeneous processes. In contrast, SnuHPL's target system is a cluster of heterogeneous GPUs. With the intra-process optimizations, SnuHPL utilizes the high-end GPUs efficiently. Also, to deal with the heterogeneity of GPUs, SnuHPL uses its data distribution generation framework, which generates the best data distribution for given heterogeneous processes. The details of the SnuHPL's data distribution will be explained when we present the inter-process optimization of SnuHPL. Compared with the previous work on optimizing HPL, SnuHPL is the first work that considers heterogeneous high-end GPUs. There exists previous work which are optimized for modern high-end GPUs such as HPL from NVIDIA or work of Tan et al. However, they do not consider heterogeneity of GPUs. Also, there are HPL implementations that support heterogeneous GPUs, but their optimization methods are outdated to run efficiently on the recent GPUs. Now, I'll explain the intra-process optimizations in SnuHPL. One problem of the original HPL is that it is implemented for homogeneous CPU-only systems. To make HPL run efficiently on clusters of homogeneous high-end GPUs, we make the following three optimizations. First, the location of the matrix data to minimize slow CPU to GPU communication. Second, intra-process workload distribution to run each phase efficiently. And third, pipelining of the four phases to minimize the idle time of GPUs. Also, there are some well-known ground rules to note. It is beneficial to keep the HPL problem size n as large as possible because a larger problem size gives better blast and communication efficiency. Also, it is important to run the DGEMs in update efficiently with minimum idle time because they account for over 95% of the entire floating point computation in HPL. First, we must decide where to store the matrix data. We can use CPU or GPU memory to store it. A common strategy of previous studies was to store the entire matrix in CPU memory, then offload the DGEM computations to GPU. They hide the CPU to GPU communication time by overlapping the communication with DGEM computation. However, we noticed that the PCIe interconnect is not fast enough to hide the communication time on recent high-end GPUs. The table at the bottom shows the minimum required MB value to hide communication when you offload DGEMs in the update phase. Such large NB values over several thousands are not desirable because it hurts the workload balance between the four phases of HPL, which impacts the overall performance significantly. Hence, we decided to store the entire matrix in the GPU's memory. In SnuHPL, each process handles exactly one GPU. The entire submatrix distributed to a process is stored in GPU that the process takes care of. For example, in the figure, there are 6 processes, so there are 6 GPUs, one for each process. These GPUs store the submatrix that is distributed to their process. It has a downside that GPU memory is usually smaller than the CPU memory, but we can minimize slow CPU to GPU communication. Previous work of Tan et al. And Kistler et al. Also takes a similar approach. The next problem is to decide which device to execute each phase, CPU or GPU. Recall the characteristics of the four phases. Fact phase consists of small and many MPI and blast routines. So the performance of the fact phase is bounded by the latency of small blast routines and inter-process communication latency. Therefore, we run fact on CPUs. In contrast, BCAS and swap phase consist of relatively large communication routines which are bounded by the inter-process communication bandwidth. We decided to run the BCAS and swap phase in GPU to exploit the high bandwidth NVLink interconnect between the GPUs. The update phase is obviously suitable for GPU since it contains a large DGEM operation. To summarize, SnuHPL runs fact on CPUs and the rest BCAS, swap, and update phase on GPUs. Now, I'll present how SnuHPL pipelines the four phases to minimize the idle time of GPU. The goal of the pipelining is to make GPUs execute DGEM computations in update phase back-to-back with minimum idle time as much as possible. It is crucial to do so because DGEM in update phase accounts for over 95% of the entire floating point computation in HPL. The main strategy here is to finish the other three phases of the next iteration before the current iteration's update phase finishes. To make the 4 phases run concurrently, each process in SnuHPL logically divides its trailing submatrix vertically into 9 chunks. The first chunk has either NB columns or 0 columns depending on whether the process owns the panel of the next iteration. The rest of the submatrix is divided evenly into 8 chunks. In this way, we can fragment the tasks of each phase to pipeline their execution. For example, even though the update phase is not completely finished, the facts phase on the next panel can start early if the corresponding part of the submatrix is updated. Furthermore, by dividing the submatrix into chunks, we can overlap the execution of the swap phase with the other phases. The update phase can start updating a chunk as soon as the swap phase of that chunk is finished. To pipeline the 4 phases, each process spawns 4 threads, one for each phase. The 4 threads run concurrently with minimum synchronization. They first wait until the required part of the matrix becomes up to date. Then they do their job, then notify the other thread that the job is complete. This figure illustrates the pipeline. It is a timeline of the 4 threads running concurrently. The arrows shows the post-wait synchronization between the threads. In this figure, the trailing submatrix is divided into 5 chunks instead of 9 for simplicity. The facts thread waits until the update of the panel from the previous update phase finishes. Then it downloads the panel from the GPU memory to the CPU memory, performs the factorization of the panel at the CPU side, then uploads back the factorized panel to the GPU memory. Bcat thread waits until the fact phase in the current iteration finishes. It also waits for the previous swap phase to finish to ensure only one NCCL kernel is running at each moment. After that, it simply broadcasts the factorized panel. Swap thread waits until the Bcat phase in the current iteration finishes. Then, it interchanges rows of the trailing submatrix chunk by chunk. For each chunk, it also waits for the previous update phase of that part to finish, so it performs a row swapping with up-to-date data. The update thread updates the trailing submatrix chunk by chunk. For each chunk, it waits for the swap phase of that chunk to finish. Then, it runs blast routines to update the chunk on the GPU side. Note that this figure is an ideal case where the workload of the update phase is large enough to fill the entire pipeline. Such ideal case occurs at the early stage of the LU factorization. As the LU factorization progresses, relative workload of the update phase gets smaller, and fact Bcat or swap phase may become the performance bottleneck of the pipeline. This completes the intra-process optimizations of SnuHPL. Now, we have an HPL implementation that runs efficiently on clusters of homogeneous high-end GPUs. We further optimize SnuHPL to run efficiently on clusters of heterogeneous GPUs. To deal with the heterogeneous processes, we modify the data distribution of the original HPL. Block cyclic data distribution is not optimal for heterogeneous processes because each process gets the same amount of workload even though they have different computing power. SnuHPL's data distribution considers the heterogeneity of processes, which includes floating point computing power, memory capacity, and network performance. It relaxes the round-robin property of block cyclic distribution, so each block row or column of the coefficient matrix can be distributed to any process row or column. One consequence of the relaxation is that there are many possible distribution options, and the number of options is too many to try every distribution by actually running SnuHPL and comparing their performance. Therefore, we need an efficient way to find the best data distribution for a given cluster system. SnuHPL uses its data distribution generation framework to find the distribution that is likely to work efficiently. The framework consists of Performance Profiler, SnuHPL Simulator, and Greedy Heuristic Data Distribution Generation Algorithm. The generation algorithm uses the SnuHPL simulator to evaluate the data distribution candidates it makes. The performance profiler provides the performance metrics required by the SnuHPL simulator. The performance profiler collects various performance metrics of every process. The metrics include memory capacity, CPU and GPU blast efficiency, kernel launch overheads, MPI and NCCR performance, and more. The performance profiler actually makes the library course with representative parameters used in HPL and measures the running time of it. The collected performance metrics are used by the SnuHPL Simulator to estimate the running time of LU factorization. SnuHPL Simulator estimates the running time with the performance model. The performance model is an analytical model which uses the metrics collected by the profiler. The performance model is built as follows. The total running time of SnuHPL is given by the sum of the execution time of every iteration of LU factorization. This gives the first equality of the formula. T denotes the running time and superscript I denotes the iteration number of LU factorization. Then, the running time of each iteration is bounded by the slowest rest in the pipeline. In the pipeline that we have discussed, SnuHPL overlaps the execution of swap and update phases with the others. But fact and bcast phases run sequentially. This gives the second equality. Now, we need to estimate the running time of each phase in each LU factorization iteration. First, the estimated running time of the fact thread is bounded by the slowest process among p participating processes. Here, small p and q denote the row and column index of a process in the process grid, and q superscript I denotes the process column index that owns a panel at iteration I. The running time further breaks down into three parts. T-PCIe is the time to transfer panel data between CPU and GPU. T-MPI is the total running time of small MPI cores in fact phase. And CPU blast is the total running time of small blast cores in the fact phase. SnuHPL Simulator estimates these small t values with the performance metrics from the profiler. Second, the estimated running time of the bcast thread is bounded by the slowest process row. The estimated running time of bcast in process row P is simply the time to broadcast the data by NCCR in process row P. Third, the estimated running time of the swap thread is bounded by the slowest column. We adopt the formula from the original HPL scalability analysis because we use the same algorithm to swap the rows of the trailing sum matrix. In the formula, alpha q and beta q denote the average latency and inverse bandwidth of NCCR and receive cores in process column Q. Note that the bandwidth depends on the data size and is estimated by the metrics in the profiler. The summation j in the last expression is to represent that the swap thread in SnuHPL runs chunk by chunk for a total of 9 chunks. The formula ignores the first chunk because its size is much smaller than the other 8 chunks. Finally, the estimated running time of the update thread is bounded by the slowest process among all. There is no communication in update, so the running time is given by the time to run dgems plus the kernel launch overhead. The time is calculated independently for every process. Again, the summation j is to represent that the update thread of SnuHPL runs chunk by chunk. SnuHPL's data distribution generation algorithm is a heuristic algorithm that generates the best data distribution for a given cluster. The algorithm uses SnuHPL Simulator to evaluate the candidates during the generation process. It is an incremental algorithm. The algorithm starts from an empty distribution, fixes either row or column direction to round robin, then incrementally chooses the undetermined row or column from last to first. To explain the algorithm in detail, please see the figure on the right. The algorithm starts from an empty distribution. Then, it first fixes either row or column direction to round robin. Suppose that the row direction is fixed to a round robin, and we have freedom in distributing block columns. At each iteration, the algorithm first determines the last block column, which is not yet distributed to any process column. Then, the algorithm generates candidates by distributing such block column to each process column, so it makes q candidates per iteration. Then, the algorithm checks the memory limit of every process and drops the candidates which violate the memory limit. The SnuHPL simulator evaluates the remaining valid candidates to get the estimated execution time for each candidate. At this point, the data distribution is not complete, so the simulator runs only for the LU factorization iterations where the data distribution has been completed. From the results of the simulator, The algorithm chooses the candidate with the minimum estimated execution time. Now that distribution of a block column is decided, the algorithm moves on to the next block column. This process is repeated until all the block columns are distributed. The algorithm keeps the distribution as the final candidate, then repeats the same process with the other direction distributed in a round-robin manner. So this whole process is repeated once more with column direction fixed round-robin, and block rows are free to distribute it to any process rows. As a result, it makes one more final candidate. Finally, the best data distribution is determined by comparing the expected running time of the two final candidates. We compare our data distribution generation method with three other strategies: block cyclic, perf ratio, and memory fill. Block cyclic is a baseline strategy as explained before. The figure at right shows an illustrative example of block cyclic data distribution in a logical view. There are two process columns, dark and light. Processes in the same column have the same floating point computing power and memory capacity. Dark processes have twice the memory capacity but half the floating point computing power compared to the light processes. Perf ratio data distribution is used in previous work, HPL GPU, by Rohr et al. It distributes the data proportional to the computing power of each process and keeps the ratio of the trailing submetric size equal as the LU factorization progresses. HPL problem size of block cyclic and perf ratio are not large enough because they cannot fully utilize every process's memory. The processes with smallest memory size bound the entire problem size. These two strategies may result in low performance because a large enough problem size is required for the optimized HPL run. Memory fill is similar to perf ratio, but it distributes the data proportional to the memory capacity of each process. The key idea of memory fill is to use all available memory. Memory fill can fully exploit every process's memory by distributing the data proportional to the memory capacity of each process. However, it does not consider the floating point computing power of the processes. Dark processes have low floating point computing power, but get more workload due to their large memory capacity. Such imbalance is kept during the entire HPL run because the ratio of submetric size does not change during the run. SnuHPL's data distribution also fully exploits each process's memory capacity. Each process column gets the same number of column blocks as the memory fill strategy, but the difference is the order of process columns that appear in the block distribution. Unlike memory fill, block columns at the beginning are distributed only to the dark process columns. So the workload gets more balanced as the LU factorization progresses. Then, after the size of the submatrix becomes proportional to the computing power of each process, the distribution of the later iterations becomes similar to perf ratio. Such data distribution of SnuHPL benefits from the large HPL problem size, while at the same time minimizing the performance loss from the workload imbalance. For the last optimization, we present a simple technique to increase SnuHPL's energy efficiency. It is done by limiting the core clock frequency of GPUs. A processor's power consumption P can be modeled as CV²F, where P denotes the power consumption, C denotes the capacitance of a processor, V denotes the power supply voltage, and F is clock frequency of a processor. In the formula, P seems to be linearly proportional to the clock frequency, but actually the power supply voltage must also increase to support the increased clock frequency. So the power consumption grows much faster than the clock frequency. In other words, we can achieve better energy efficiency by adjusting the clock frequency of a processor. As a preliminary experiment for energy efficiency optimization, we measured the energy efficiency of DGEM kernels on NVIDIA GPUs with different core clock frequencies and different power consumption limits. The experimental results confirm that the maximum performance does not give the best energy efficiency. For example, the sweet spot of the V100 GPU's energy efficiency is at around 50% of the maximum power consumption limit or 80% of the maximum core clock frequency. Since over 95% of the computation in SnuHPL is done at DGEM kernels, we can expect to increase the energy efficiency of SnuHPL by applying the exact same method. The evaluation of SnuHPL is done on two types of GPU-based clusters. The first type is small clusters. Each small cluster consists of 4 nodes connected by an HDR InfiniBand network and can have 4 NVIDIA V100, P100, or Titan GPUs. Small clusters have various node configurations to test how well SnuHPL performs on clusters of heterogeneous GPUs. The second type is the large clusters. The large cluster is Samsung's SSC21 supercomputer and its variants. Each large cluster consists of 18, 220, or 440 nodes connected by an HDR InfiniBand FAT3 network. Each node in a large cluster can have 8 NVIDIA 800 80GB or 2 NVIDIA 800 40GB GPUs. We first evaluate SnuHPL on Samsung's supercomputer SSC21, which consists of 220 nodes and 8 NVIDIA 800 80GB GPUs per node. SnuHPL achieved 25.18 petaflops with 70.2 floating point efficiency. As you can see in the figure, the floating point efficiency only drops about 6% from a single node to 220 nodes, so SnuHPL is scalable to the large clusters of modern high-end GPUs. Also, the SnuHPL simulator estimates the running time of the SnuHPL on large clusters quite well, with an error margin of 5%. With this result, SSC21 is ranked at 11th place in November 2021 Top 500 list. Then, we evaluate SnuHPL's heterogeneity support on various clusters of heterogeneous GPUs. Left 6 results are the evaluation on the small clusters, and the rightmost one is the evaluation result on the SSC21 extended supercomputer. SnuHPL's data distribution performs the best for every cluster except for one, which is cluster F. It is the case where GPUs with small memory dominate the cluster, so block cyclic data distribution is already near optimal. The SnuHPL's data distribution for heterogeneous GPUs achieves 1.17 times speedup over the block cyclic on the SSC21 extended supercomputer. We can expect this result from the results of cluster C and cluster D, where the number of GPUs with a large memory capacity is much bigger than the number of GPUs with a small memory capacity. To summarize, SnuHPL's data distribution outperforms the other data distribution strategies. Also, the SnuHPL simulator again estimates the running time pretty well with an error margin of 5%. SnuHPL's 29.0 petaflops and 66.2% floating point efficiency on SSC21 extended is comparable to the performance of the 10th fastest supercomputer in November 2021 Top 500 list. Finally, we evaluate the proposed energy optimization technique on SSC21 scalable module. The power consumption is measured at the PDU that supplies power to all the 18 nodes and an HDR InfiniBand switch. As expected, the performance of SnuHPL increases as the GPU power limit or clock frequency increases. However, the energy efficiency is not proportional to the performance. We achieved the maximum energy efficiency of 33.98 gigaflops per watt at a GPU clock frequency limit of 1100 MHz. With this result, the energy efficiency of SnuHPL on the SSC21 scalable module is ranked second in November 2021 Green 500 list. It is the most energy efficient supercomputer in 2021 with general purpose GPU. In conclusion, we present SnuHPL, an optimized HPL for clusters of modern heterogeneous GPUs. We first presented intra-process optimization of HPL for clusters of high-end homogeneous GPUs. Then, we presented a data distribution generation framework for SnuHPL to work efficiently on clusters of heterogeneous GPUs. Finally, we proposed a simple energy optimization technique which can greatly increase the energy efficiency of SnuHPL. We believe that the described optimization methods can be directly applied to HPLs implemented in other programming models such as OpenCL. Also, the energy optimization technique is totally independent of HPL, so it can be directly applied to any other GPU application. This is the end of my presentation, and thank you for listening.